And you cannot do it because you don't know how to read the chart, but because you didn't write that number in. You may tell your friend who missed this class, but you don't need to, okay? So what about Kelvin? You need to know how to change from Kelvin to Fahrenheit? You may not need to memorize, but write it down to do information change. So this unit conversion, you need to write it down. Another way of looking at hydrate phase envelope, we can predict it based on gas gravity. This is 0.6, 0.7, 0.8, 0.9. Okay, how much is the methane molecular weight? KTS Ramirez. KTS Ramirez. How much is methane molecular weight? About 16? Are you like 17? Around 16. So methane is 16. Why some gas have the specific gravity of 0.9? What happened? What do you think happened that make gas have higher specific gravity, Kathy? You agree with him? Or what did he say?
He said it's heavier.
How come methane become heavier? Okay, let me ask you this question. When you produce from the reservoir gives you pure methane, is that correct? Will it give you propane, butane, maybe C5, C6, a little bit, maybe C2? It gives you all things. Can it give you carbon dioxide? Is carbon dioxide heavier than air or not? No? Who's no? Okay, so what's your name?
Zach.
Zach, what is the molecular weight of carbon? 12?
Yeah.
What about oxygen? 16. Oxygen twice, 32. 32 plus that becomes 44. 44 is more than 29 or less than 29? Yeah, so carbon dioxide is kind of heavier. I mean higher density than air. Okay, so if you have methane plus carbon dioxide, your gas molecular weight, I mean gas gravity can be 0.8, 0.9 or something. It could be more than 1. Now you believe me, Zach? You believe me now? Yeah, okay, right. Okay, here's another chart that's in PSIA. Maybe this help you a little bit. Okay, this is in Fahrenheit. So if I have the pressure before the line heater, about 2000 psi, pretty high. So this tells me at about 59 Fahrenheit, we will form hydrate. 59 and below. So if I have gas coming in at 2000, it's pure methane. We have gas coming in at 2000 psia, and my temperature is 70, I'm fine, I don't form hydrate. But if I'm at 50, sometimes level land get a little bit cold. We have like snowstorm, we have snow sometimes, so it's a little bit cold, we may form hydrate. Okay, and that may not be good. Okay, this chart can tell you that. Do you know how to read the chart? It is going to be in the exam somehow. Okay. Yes, no question on the chart? Okay, let's move on. Preventing, how do we prevent it? We avoid it. We don't want it to form. Okay. We may avoid going inside the hydrate phase envelope, or we put inhibitor in, or we remove water, dehydration. How do we remove water? I know that I didn't teach anything about that yet, but what do you think? How do we remove water from gas? Dehydration you didn't have. What is the chemical inside? Is it green? Maybe it's not green. Yes, it is glycol. We can use glycol to remove water. So to handle this hydrate, we can use line heater. Line heater happened in the test a couple years ago. I asked line heater is direct heating unit or indirect heating unit. Many people fail, so it's indirect fire heater. Okay, it's indirect heating. So it heat the gas stream before, okay, And it could be or after the shock, mostly before. Sometimes, very rare is after, but most of the time it's before. So that gas maintain above hydrate temperature all the time, both before and after choking. So when we choke, the temperature will drop. How much will the temperature drop? 10 Fahrenheit? Kenny, how much will the temperature drop from hydrate? 11?
It's going to depend on the temperature drop or the pressure drop.
I don't know either. We look at the chart. Okay, the chart will tell us, but we don't need to know how to read the chart. Another unit is LTX, low temperature exchanger. So this one is operate in a different way. It let hydrate to form and use the heat from the flow itself to melt it. Okay, temperature of the well stream to melt the hydrate after they form. So it let hydrate form. Temperature drop calculation, this is about JT cooling. It's not always cooling. When at the high pressure case, when the pressure drops, it can be hotter. Okay? But most of the time, at the lower pressure case, when the pressure drops, it's cooling. Most of the time it's cooling, but it can be heating too. And I will show you in the boiler diagram to show you what case that it will heating. Okay? One thing that you need to memorize. Pressure drop across the choke is constant enthalpy process, or can roughly assume that it's constant enthalpy process. It appears every quiz, every exam, every year, so put that in. Constant enthalpy means capital H, say the same. There's no heat putting in or heat loss during that short distance, okay? So at the shock, it just go through the restriction and the pressure drop a lot, but we didn't put any heat on it, or we assume no heat loss. So we use Euler diagram or maybe pressure enthalpy chart to find out. If we have multiple components, if we don't use the chart, we use the software. So in this class, we teach you how to use the chart. Okay, this is the chart. This is a pressure enthalpy chart. We say, hey, the one that you get in the exam will be bigger and it's readable, okay? This I know that it's not quite readable. So let's take a look at pressure drop from 4,000 psia to 1,000 psia. Temperature will drop from 120 Fahrenheit to what temperature? First, assume that we use the right chart. Okay, this say methane. Methane pressure enthalpy diagram. If you don't have pure methane, you have natural gas, specific gravity of 0.7, use the chart that is for 0.7. Okay? So this means you need to know how to calculate specific gravity of gas. Okay? Who know that or who don't know that? Maybe my question is not quite specific. If I have 90% methane, 10% carbon dioxide. Do you know how to calculate average molecular weight? You think you know?
Yeah.
Okay. Who don't? We will have the lecture about that, but it is important, okay? Alright, because if you cannot know that, you don't know which chart to use. I give you 5 charts, you use the wrong chart, the answer is wrong, you say with me here. Okay, how do we read that? First, we need to know which line is which line. You see the red line over there? That one is a constant temperature line. So this axis is pressure. So that red line is a constant temperature line. Okay. The horizontal green line is a pressure line. The place where red cross with the green, that is your starting point. We start at 4,000 psia and 120. Okay. We have pressure drop across a choke, which is constant H or constant enthalpy process, enthalpy doesn't change. So we just move down vertically, right? Until we meet with the line that has pressure of 1000 psia. And then we read the temperature by use the purple line. The purple line says that is 40 Fahrenheit. Then we know that temperature will drop about 80 F. Good? Next method. We can use this chart for the quick approximation. So this chart talk about temperature drop. Okay. Initial pressure, PSIG. Okay. So this chart from, I think from GPSA. So how do we do that? We start from 4000 PSIG. How much is the pressure drop? This line on the curve side is a delta P. 4000 minus 1000 is delta P of 3000. So we select this line, delta P of 3000. Okay. I move up, reach that point, move to the left, and read the temperature drop. Temperature drop over there say 80 Fahrenheit. Wow, this chart tells you the same thing as this graph. It's nice, isn't it? Is it? It's not nice. You don't see that it's beautiful. You like it? You want to learn, okay. So when you, there's a correction factor. Look at this part. Approximate temperature correction for hydrocarbon that contain water. This is barrel per mm CF in stock tank. Mm here means 1 million, right? Okay. Don't get confused between this mm and this M. What is that MPa? Megapascal. It's not 1000 Pascal. Right? Okay. There's a correction factor. It says if we produce water with it, what do you think will we have more temperature drop or less temperature drop if we produce water along with it? More. Raise your hand. Raise your hand, okay. Leonardo. Yes. Okay, Leonardo. More or less? If you produce water with it. Temperature drop. Will we have more temperature drop or less temperature drop? Less. Okay, let's take a look at this. More liquid condensed, less delta T. Yeah, correct. So what happened is we use a correction factor. If oil production is 20 barrel per mmCF, no correction factor is needed. If we don't produce any oil, correction factor is minus 10. So what I did is 120 minus 80 and minus 10. So we totally have 90 Fahrenheit drop if we don't produce anything. So it may be a little bit like difficult to to read, but make sure you understand that if we don't produce any liquid along with it, we have more temperature drop. If we produce a lot more liquid, we have less temperature drop. And next, Christian Dominguez, what is that? What is a Christian?
Heat through the fluid, I'm guessing.
What?
Heat transfer through the fluid.
Heat transfer to the fluid. What is how much is specific gravity? Oh, I'm sorry. CP, specific heat of water.
So what?
Specific heat capacity of water. Or how much energy do you need to raise the temperature of 1 kilogram up by 1 Kelvin? We have water, 1 kilogram of water. I raise it up 1 Kelvin. How much energy in Joule that you need?
You raise it up to 1 what?
Kelvin. What is Kelvin? 1 Joule. I think I tricked you, okay? If you have 1 pound of water and you raise it up by 1 Fahrenheit, I think that would be what 1 BTU or something. But this SI unit is 4,000 something. You need about 4,000 joules to raise the temperature of 1 kilogram of water up by 1 Celsius or 1 Kelvin. Okay. System P of water is more than the gas. So it can resist the change better. It doesn't want to change. We need a lot more heat loss to change the temperature of water than to change the temperature of air or gas. Okay, because of specific heat capacity mainly. So if we produce water with it, we don't have much temperature drop.